So in this section, we're going to look at the phenomena of breakdown and reverse bias of p-n junction. So the phenomenon is that if we have our current and voltage like this, and we apply sufficient reverse bias, eventually the current will go to infinity for infinitesimal additions of reverse bias. So effectively what this means, we can use a p-n junction held in reverse bias as a voltage regulator. So it'll keep the same voltage no matter what current's flowing through it. So this happens through two mechanisms. This breakdown in reverse voltage happens in two mechanisms. One is Zener tunneling, and two is avalanche multiplication or impact ionization. Okay, so let's look at both of these mechanisms in turn. So first, let's take on Zener tunneling. So the idea behind Zener tunneling is that we're going to consider an electron actually in the valence band. So this is one of the electrons that's actually involved in the atomic bonding between silicon atoms, let's say. So we've got these electron pairs binding our silicon atoms. And if the field becomes high enough, if we apply a large enough electric field over this region, what can happen is one of these electrons in one of these bonds can actually be ripped out and go that way. And because there's an E field, the hole it leaves behind will also start moving. So on this energy band diagram, what that looks like is tunneling of an electron between where it was fixed in place at this silicon atom and then being allowed to move through the crystal, and also the hole which it left behind being accelerated that way. So remember what's happening here is actually a field ionization, and it's a generation of an electron hole pair event. Now we have to look at the energetics of this. So in order to get from here to here, this electron here actually had to tunnel through an energy barrier. And the approximate way that we usually treat this is to consider the tunneling barrier to be approximately triangular. And of course, it's really given by this curved shape, but to make our model work out easier, we can just imagine that it's a triangle. So the height of this tunnel barrier is the band gap, and its width is, surprise, surprise, the depletion width. Now, if we remember back to our discussions of tunneling, the probability of tunneling through a rectangular barrier has a prefactor and then an exponential term. Of course, the details are a little bit different because it's triangular. Let's just look at that exponential term. So for thin barriers, we usually write the expression like this, that the tunneling probability is exponentially sensitive to the width of the barrier. So in the chapter on tunneling, we called this A, but here we can write it as WD. So the last thing we can remember here is that our depletion width is actually a function of the voltage. And so if we apply larger and larger reverse bias, so reverse bias makes the slope here higher and higher, and it shrinks the depletion width. And as this depletion width is shrinking, it means the probability of tunneling will take off exponentially. And lo and behold, that's what happens here also. -2 times alpha times WD of V. So Zener breakdown, the microscopic physics is field ionization of an electron out of an atomic bond, and then tunneling of that electron across the depletion width in space, but also across the band gap in energy, because the band gap is sloped so high, moving from here to here actually represents a transition across the band gap. So the second mechanism is impact ionization. So physically, impact ionization requires a first event. So we can imagine we have a highly reverse biased p-n junction like this. And in terms of the E field, we're dropping a lot of voltage over a short distance, so we have a large E field. And we have to remember when an electron is in an E field, it will be accelerated and move in that direction, and its velocity will be given by mu E in the low field range. At high enough E fields, this velocity becomes V saturation, and remember that's about 10 to the 7th centimeters per second. So it turns out if they get going fast enough, the energy, the kinetic energy, is going to be at some point larger than the band gap. And if this happens, we can again picture a silicon atom. It's got 2 electrons bonding it to another silicon atom. And then we come in with this really fast, high kinetic energy moving near the saturation velocity. And that can actually create a collision which liberates this electron also. So now we've got 2 electrons and then also 1 hole. So we have our original electron as well as this other one that we generated. So this is why it's called impact ionization. Literally, one electron hits another one and gives it enough kinetic energy to move across the band gap. So what we've done here with this electron is actually promote this other one up on the band diagram, and then the hole moves that way. This can actually create a chain reaction, just like a nuclear chain reaction. Each of these electrons can now go on to liberate other electrons, and so the number starts branching, and you get exponential growth. So from one starting electron, at the end of the day, you can get a very large number of electrons reaching the other side of the p-n junction. So let me first talk about applications for a second. This can be used to good effect in what it's called avalanche photodiodes, or APDs. And in this case, we would imagine that this original electron was generated by the absorption of a photon. And then it goes on, the single electron would be a very hard thing to detect with an oscilloscope outside of the junction. However, this cascade of electrons that's generated by the impact ionization chain reaction can result in a very large current pulse. So current is a function of time. So on your oscilloscope, you can actually see single photons being captured by this photodiode because of this internal gain, this gain which is given by the multiplication ratio inside of the depletion width. So avalanche photodiodes are used nowadays in especially low light conditions, or also for counting single photons. Okay, so we've talked now about the microscopic mechanisms behind impact ionization. Let's look at their effects on current through the diode. So we're going to imagine that we have a depletion width, and we can inject a tiny bit of current at the left-hand edge, and this is going to be the current carried by electrons. So because of that exponential growth, the current through the diode is going to grow exponentially and eventually reach some value at the other side. Similarly, if we have a whole current, it's going to start at an initial value on this side and then also grow exponentially, because no matter which particle starts the avalanche cascade, in every ionization step you're generating one of each type of carrier. So in steady state, the total current is going to be constant, and it's going to be given by the sum of the hole and electron currents. So what we want to look at is, at some point here, we can look at what the change in the current is going to be. And for each infinitesimal volume unit, the current is going to be proportional to the existing current at that point for both electrons and holes. And this is the coupling part, because the electron current, remember, is also going to be dependent on the hole current, because if a hole ionizes an electron-hole pair, you get one of each. The total current, as we said, is the sum of both of these. So we can use this to rearrange the formula and get an expression that din of x dx. Oh, excuse me, I forgot to multiply through by my infinitesimal volume distance elements. So this is going to be the in of x itself times the sum of these two, alpha n plus alpha p. And then we're just going to say this is given by alpha p times I total. And remember, this is a constant. So if we can assume that these two are equal, and just give a single alpha, then we can get an expression that in, and we're going to integrate from here to here. So in at the edge of the depletion width. Okay, so now let's try to figure out something about the gain in a diode in avalanche breakdown. Let's say the gain factor for an APD that I talked about. So one thing we can notice is that at the depletion width edge here, the total current is almost entirely given by the electron current, because the whole current at this point is very small. So we can write I tot is about equal to IN now we can also say that IN at 0 times this multiplication factor we're going to define, or this gain factor, is going to be given by IN at WD. So this multiplication factor is, in essence, this ratio between this value and this value. So if we substitute into this part of this equation down here, we can see that this IN of WD is IN times M, and then minus I naught of 0 itself. What do we do about this total current here? Well, let's approximate it by IN of WD here. And this is also going to be equal to IN of 0 times, again, this multiplication factor. So we've used these two parts here, defining the multiplication factor and making this approximation. So if we simplify this, bringing this one over, we just got rid of the total current. And we can simplify this to 1 minus 1 over M, if you look at this, and then pull out the factors of IN of 0. Okay, so this integral is what we need to deal with. So you see that this alpha is going to have something to do with the material properties, but this depletion width has to do with how we construct the diode. So different diodes are going to have different depletion widths and thus different gain factors. For example, if the diode is very long, there's a lot more chance for this avalanche multiplication to happen, and the gain should be higher. So in fact, if we're looking for high gain, if N is very high, if M is very high, we're looking for the condition where M goes to infinity to get a very large gain. That'll mean that this right-hand factor here is approximately going to 0. So the condition for finding out if we'll have a very large avalanche multiplication effect, and actually in terms of the IV curve, where our breakdown voltage will actually be. Here's our IV. If we want to find out where that breakdown voltage is, we're going to look for the point where the multiplication factor gets very large. And thus, we're going to look for the point where 1 minus 0 is the integral from 0 to WD. And remember, this is voltage dependent, dx. We can then use this criterion to find out the breakdown voltage. We replace that applied voltage by the breakdown. So now let's try to link everything together so that we can figure out a relationship between the material we're using and the breakdown voltage at which this avalanche multiplication will happen. So let's imagine we have a P plus N diode. So the depletion width is basically entirely in the N-type region, which is doped with ND. NA is much bigger than ND. Also, let's assume that your reverse bias is much, much larger than the built-in voltage. This allows us to write the depletion width on the N-type side as approximately, and we're dropping the built-in voltage here. At the breakdown field, we can actually define this V reverse as the breakdown. Now, for this p-n junction, our Emax, our electric field maximum occurs here at the metallurgical junction. And this is given by Q and D. So putting these together and then solving for the breakdown field, we eventually get that V breakdown is. So this E critical here is related to the material properties. So the properties of silicon or gallium arsenide, etc. The doping here appears, so obviously your breakdown field will go down for higher doped diodes. And this E critical is our attempt to come up with a material property that can be used as a design criterion. For example, if we want to make a APD, we would look up what the critical E field is for the semiconductor like gallium arsenide, and then use it in our design. And the rest, it has to do with the electrostatics of the p-n junction. Okay, so that wraps up our treatment of breakdown and reverse bias for the two major mechanisms, Zener tunneling and avalanche or impact ionization.